Hey everyone, we're here for our next talk. We have Claudia, Chief Scientist at NIM. She'll be doing a talk on why we need network level privacy, P2P, Tor, and Mixnets. And I'll let her take it from here.
Thank you very much for the introduction, and hi everyone. I'm very happy to be speaking today about network level privacy. So first of all, I guess many of you know that on-chain protection is necessary but not sufficient. So by now, we know that blockchains such as Bitcoin leak information at the chain level that can be used for tracing transactions, right? But even if we have better systems that provide more protection at the chain level, underneath any blockchain, there's going to be a communication infrastructure, because this is basically a common ledger that is maintained by a set of computers that have to talk to each other. They have to share information in order to make this blockchain grow and happen and be maintained. So the problem is that the network level protocols on which we rely on, I actually expose metadata by default. So what do we mean by metadata? Who sends the information, what's the destination of the information, at what time is sent, how long, how many bytes are in the data, and any other features that we can extract from the data flow. And when we have data flows that contain multiple packets, we might be able to extract patterns from it. So basically, what has been shown in prior work, and Alex Virjukov from University of Luxembourg and others, they have done a lot of work on that, is that you can, by looking at the timing of messages exchanged at the network layer, you might be able to cluster transactions as belonging to the same person or same account. You might be able to link the IP address of the person who made a transaction to the transaction itself, meaning that you are able to de-anonymize it. And what this means is that even when you are putting a lot of effort to make very sophisticated, very nice protocols that protect private data on chain, such as the ones used by Zcash or Monero, the problem is that if you're not using any protections at the network layer, the metadata can be exploited to undermine these on-chain protections. Effectively, it functions as a side channel, because it's out of the scope of the assumptions of the on-chain protocols. So what about payment channels such as Lightning Network? One advantage of Lightning Network is that you don't really have a persistent public record for each transaction as you have in Bitcoin, for example. So this is better for privacy because you have a lot less exposure of these transactions being available to everyone in the world forever, effectively. But and Lightning also takes care of protecting network metadata to some extent. It is based on the Sphinx packet format. Sphinx is a packet format for layered encryption that allows you to do multi-hop routing in networks, such that you have bitwise unlinkability. What does this all mean? It means that with Sphinx, you will be able to put multiple layers of encryption. This is similar to onion routing, similar to what Tor does, with each intermediary removing one layer of encryption. And this is designed in a way that if I am able to see the incoming packet and the outgoing packet, there is no information in the packet that will allow me to correlate an input to an output. So you get perfect unlinkability in terms of the bit patterns. However, you can still link inputs to outputs based on order, based on timing. So in Lightning Network, for example, these nodes, even though they are transforming cryptographically the packets that they route, they are not doing any mixing, meaning that they are not delaying them in order to make them confused with other packets that they might be routing at the same time. So that means that there is no protection against global passive adversaries. So if you look at this figure that is in the slide, if, for example, the red node is making a transaction with the green node, a global network adversary would be able to see that the red node has not received anything and has initiated a packet that goes to the first orange node that then is immediately or after a few milliseconds forwarded to the next orange intermediary that forwards to the green, and then things come back. So this is a very distinctive pattern that would enable a global passive adversary to know that actually the payment is being done between red and green. And even if you have private channels, like in the right side of the figure, you would be able to see like a distinct exchange of packets in terms of the numbers of packets that go in each direction that would indicate that those two nodes, even though you don't have knowledge of them having a channel with each other, are conducting a transaction, which would reveal the existence of that channel. So basically, by looking at the inputs and outputs, when they come in and come out, you might be able, as global adversary, to correlate inputs, outputs, and trace transactions end to end, meaning that you have no anonymity, which is something that Lightning would like to provide. There's also quite low anonymity with respect to intermediaries. So the intermediaries here would be the two orange nodes. And ideally, the first orange node should not be able to determine whether red is the originator of the transaction or whether red is just another intermediary that is forwarding the transaction for somebody else. And similarly, the second orange node should not be able to know whether green is the other end of the transaction or whether it's, again, an intermediary that will continue to forward the transaction. However, you have to see that if red, the first orange node can, for example, make the conclusion that if red is not the originator, but rather the originator is one of the two blue nodes that are connected to red, if those two nodes were initiating a transaction with green, they would not go through red because that would mean paying more fees to an intermediary that is not really necessary, in the sense that the one that is below would directly go to the second orange node, while the one that is up will go to the first orange node. So in no case would they be routing through the red. So that means that if something is going from red to the second orange, it is very highly likely that red is the originator. So that means that the anonymity set of possible originators is very small in Lightning. This is because the network is sparse, so not everybody is connected to everybody else, because you want to optimize routes in terms of them not being very long, so taking the shortest, the most efficient route. So that means that there are not so many options, and it's not like you have a lot of uncertainty on whether your successor or predecessor are one of the ends of the connection. So what does it mean to have network level protection? What do we want to achieve, actually? What kind of properties would we like to have? So there are many network privacy properties that we might desire. Just to give you a sense, I'll go one by one on this, and I just want you to know that this is already not exhaustive, in the sense that people that go into formalizing properties, they will, define many more to fit all kinds of scenarios with all kinds of side channel information and so on. So, but these are some of the important ones that we want to achieve. So one is third-party anonymity. So what does that mean? When we have third-party anonymity, if I'm exchanging messages with you, it means that you and I might be authenticating each other. We know who we are, but we don't want other people, third parties, to know that we're talking to each other. So this is kind of the most basic anonymity property, in which the two ends, they don't want to be anonymous to each other, but they want to be anonymous in the sense that other parties cannot determine that they are talking. This is typical, for example, in messaging systems. I don't typically exchange messages with random people, anonymous people I never met. I exchange messages with people I know. And if I want privacy protection, it's not so much towards the person I'm talking to, but it's towards network operators or other parties. Sender anonymity is it's kind of it's very simple. It means that I'm able to send you a message through the system, and you should not know who I am. You shouldn't be able to tell where it's coming from. That's relatively simple. Typically, systems that have third-party anonymity will also provide sender anonymity, but sender anonymity by itself is not terribly useful, because if my system only provides sender anonymity, I might be able to send you a message, but you would not be able to reply to me and reach me back. So that is kind of functionality is quite restricted. So you might want to also have recipient anonymity. That means that you're able, when the system provides me with recipient anonymity, it means that you're able to contact me without knowing my IP address or my network address or identifier, right? So this is, for example, what you achieve with Tor hidden services, that you're able to contact the service without actually knowing where it is located. Another property you might want to have is unlinkability. So that means that you're not able to tell that multiple transactions belong to the same individual or account. So this would prevent clustering of transactions. If you want to have even stronger privacy protection than what you get with anonymity and unlinkability, you might want to have unobservability. This means that I am not able to tell when and how much you're using the system. Typically, this is obtained by using dummy traffic, meaning that even when you're doing nothing, you're kind of sending traffic to the network in a way that when it's not possible for somebody who's looking at your connection to tell apart the cases when you're not doing anything and it's just automatic traffic and when you're actually sending information. So that is already much costlier to achieve and is more difficult than anonymity and unlinkability. And then the strongest property we can aim for is undetectability. This is actually extremely hard. And this means that I am not able to tell whether you're accessing the network, right? And this has to already use different kinds of techniques, steganographic access, and so on. So this is actually a pretty hard problem. Two more properties you might want to have in network privacy is forward security. Typically, you consider that some of the participants might be compromised or the keys might be leaked. So you don't want that to compromise too many communications, in particular communications of the past. And because these are distributed systems, it's not acceptable to make an anonymity system that depends on one big trusted third party, because that basically means that if that party is compromised, your whole privacy is gone. So you typically will need to distribute trust over multiple entities, and this is why there is multi-hop routing, because you're distributing trust over all the hops in the route. In terms of adversaries that you want to protect against, there's at the network level, so adversaries that are operating the internet infrastructure and who are able to observe traffic on the internet. You can consider global adversaries, means that they can look at the full internet, the whole world. And some systems are designed for local adversaries that are only able to see, some points in the network. Maybe they're only able to observe the sender, for example, but not beyond the sender. They don't know what kind of traffic is observable. Of course, if you're designing a system that is decentralized, that has a number of participants that collaborate together to provide a service, you have to consider that some of these participants might be adversarial, that the adversary might be able to generate some of these participants and insert it into the system. So you should be able to provide privacy properties, even if some of the participants are corrupted. I say subset. Obviously, if all participants are corrupted, then it's game over. Will not be able to obtain anything. But assuming that you have some honest and some adversarial, the question is how strong you can make your system so that the adversarial ones are not able to break your system to attack it. And in terms of method, when we do traffic analysis and network privacy, we are not so much looking into proofs or formal proofs of security, but we're more looking into statistical analysis metadata. So the adversary will have some visibility on some of this data, meaning see packets that coming to some participant, that come out of some participant at a certain time with a certain length, and so on. And the adversary will collect all these observations and then do statistical analysis in order to correlate inputs to outputs, senders to receivers, find relationships between transactions that belong to the same user. All right. So anonymous communications architecture, they aim to provide at least some of these properties, in particular anonymity properties. And we have different types of systems that can achieve this, right? And I put here some of the most salient types of systems, notably onion routing networks. I'm sure most of you are familiar with Tor, which is the kind of most prominent implementation of onion routing. There are mixed network designs. We at NIM are designing one. Elixir is also designing a Mixnet. And if you want to go to classical systems already from the early 2000s, Mixmaster was a remailer, a system for anonymous email that was implemented already almost 20 years ago. And in terms of peer-to-peer designs of deployed systems that I'm aware of, there is I2P, there is Hopper, and then there's a large number of systems proposed in the literature, but are just theoretical designs that haven't been really implemented. So before I go into talking about the differences between these architectures, I want to say about what's the same for all of them. So these are all typically overlaid networks. Okay, so that means that between every two entities in the system, they're basically communicating through the internet. And from the point of view of the internet, this is an end-to-end communication. Of course, then you do multi-hop routing, which means that you kind of put together various of these pipes in order to have, something end-to-end that is not easy to link. And all of these systems also do multi-hop routing. So your information will not go directly to your recipient, but in order to achieve anonymity, you will send it to intermediaries that will kind of forward it on until it gets to the recipient. And then another thing that is common to all of these architectures is per hop bitwise unlinkability. So that means that if you are looking at the messages coming in into a participant, into a node, and you look at the messages coming out, by the bit pattern, you should not be able to relate inputs to outputs. So there shouldn't be some sort of identifier that is the same in the input at the output, or any sort of distinctive identifier or distinctive length that you can use to relate inputs to outputs. So this is achieved in onion routing through the decryptions and Sphinx, which is a packet format that a lot of designs use. That all the designs that are packet-based use Sphinx, as far as I know, also provides the same. Okay, but how are they different, onion routing and Mixnets? Okay, so I'm just going to emphasize some of the main differences between Tor and Mixnets. So one of the big things is that Tor and onion routing is circuit-based. Okay, so basically you have a first phase in which you create a circuit. To create a circuit, you use public key cryptography. I select typically a few intermediaries. 3 is a number that is used very often, so I will select 3 intermediaries, and then set up a circuit that goes through these intermediaries to my desired recipient. And I will use public key cryptography in the circuit creation phase. This is also used to establish symmetric secrets with each of these intermediaries. And then once the secret has been created, the data transfers, they make use of the symmetric keys that have been established in the circuit creation, and this means it's all very fast. Now, it's very fast and very efficient, but of course, this comes at the price that you have linkability of all messages within a data flow. Okay, so all of the intermediaries, they know that any 2 packets that are sent within the same circuit, they come from the same sender, they're going to the same destination, and they are related to each other. In Mixnets, on the other hand, the routing is message-based or packet-based. You can choose your terminology. So that means that you have to do public key crypto per packet because you don't establish any share secrets with the intermediaries. So you basically send kind of you have to use public key crypto per packet in order to transform this packet in a way that only the chosen intermediary can do the transformation, and others cannot infer any information if they don't have the key. This provides a linkability between any 2 messages that I send, even if I'm sending them through the same path, which I would not normally send them to the same path. But if by chance I would choose the same path for 2 of my messages, intermediaries would not be able to tell that the 2 messages are coming from me and that they're related to the same connection. So here, this is already one element in which Mixnets provide higher privacy at the cost of more overhead, in this case, computational overhead. In addition, Tor and onion routing doesn't add any latency, so it's basically first in, first out. It tries to forward messages as fast as possible. And this is in part done because adding latency has a huge impact on usability. And you only want to do it if you really understand what you're gaining with this cost, right? And in onion routing, because you have all this linkability within the flow of a circuit, it is not easy to see how much you would gain with latency. I mean, if you start kind of delaying some messages within the flow, more or less, to what extent would that be enough to make it really unlinkable at the flow level, right? And you might have to incur in a very heavy usability cost in order to have some meaningful protection. And it's hard because you have all this linkability information that makes it very hard. In Mixnets, on the other hand, because every message is treated independently, routed independently, encrypted, with different keys, you can add latency per hop and then achieve unlinkability per hop, not only based on the cryptographic appearance of the packet, but also on the timing of arrival, departure, and basically the ordering of messages, right? So here's another case in which we are achieving much higher security. In this way, in this sense, if I am observing a mix and I see messages coming in and coming out, I cannot tell which input corresponds to which output. While in Tor or in onion routing, I might be able to link inputs to outputs based on the timing, not based on the not based on the appearance, because the crypto destroys that, but based on the timing. So here's another case when you get higher security at additional cost. In this case, the cost is latency, and you have a very clear trade-off for a given traffic load. You will have a very clear trade-off between latency and anonymity. In that, if you increase latency, you will achieve more anonymity. That's basically because for every input, there will be a larger number of outputs that could correspond to it. If you can incur in higher delays than not. So this is like a design parameter. You have to know where you want to be in this trade-off. In onion routing, a bit for the same reason as for adding latency, it is hard to design effective dummy traffic strategies, right? In the sense that you have all these very rich features in a traffic flow. So if you want to add dummy traffic, how much dummy traffic do you need to add in order to make two flows kind of be possible to be confused with each other? And I've done a lot of work in website fingerprinting, and I mean it's quite informative to see how much information, how many features there are in these flows, and you have to use some substantial amount of dummy traffic if you want to start having some level of protection there. In Mixnets, again, because packets are independent, it is easier to design dummy traffic strategies and raise the level of protection that you are obtaining. You raise it in two ways. First of all, by having more traffic load, you will have bigger anonymity sets. So anonymity improves with more dummy traffic, but you also might be able to achieve unobservability properties in the sense that I may not be able to tell when you are actually conducting a transaction or not, if you are sometimes sending traffic even when you're doing nothing. So all of this means that onion routing and Tor is designed to consider an adversary that is local, meaning that the adversary can observe either the sender side or the receiver side, or maybe some point in the network, and you have some protection against such an adversary, but not against a global adversary that can see all traffic in the network. Well, Mixnets actually can provide you with that kind of protection. They are designed to be secure, to be private, even if the adversary can see all the internet links that are in use by all these participants. Okay, so how do now, I want to now talk about peer-to-peer architectures versus client-server. And by client-server, I will consider Tor and Mixnets as being client-server, and peer-to-peer is, systems that actually have symmetry of roles between all the participants, right? So, what is key to me about the first key point that distinguishes these two types of systems is that in client-servers, you have a distinction of roles. You have clients and you have infrastructure nodes, right? And to me, this is really key because in a privacy system, you want to have as much privacy as possible for clients, while at the same time, you want to have as much transparency as possible for the infrastructure, so that you're able to see whether the infrastructure is behaving as it should. You're able to see that that they are not doing anything malicious, and you're able to know who they are and decide of whether you trust these infrastructure pieces or not, right? So in peer-to-peer, there is this merging of roles in which everybody is everything. Every node is both a client that will be initiating or receiving connections, but they are also infrastructure that route connections for others. So this kind of puts you in a world of trade-off where either you make more information about each of these participants publicly known, you distribute this information, and that will help transparency, will enable me to better choose intermediaries, for example. But at the same time, this means that you have to expose these clients as infrastructure. So you will run into problems such as client enumeration, right? Like if all the nodes in my network are also infrastructure, they need to advertise themselves to others. They need to be able to be contacted by others. So that means that their IP addresses will have to be publicized and distributed and so on. So this already puts you in a situation that's a bit undesirable, because you might want to not expose the IP addresses of clients to everyone, right? You will have to expose them to somebody, to some entry part of the network. But I think there is a difference between having to expose them to the entry mix or entry your guard node in Tor, compared to having to kind of publicize the information for everyone. So that's one distinction. Another distinction is that in client server, you typically assume that the clients have full knowledge of the network, well, clients and servers as well, so that there is some common knowledge on the full network, right? Of course, this introduces a little bit of overhead, because if you have a very large network, you would have to download all these node descriptors, and if the large network has a lot of churn, then that overhead can become significant. And some people have, for Tor, they have proposed recently this walking onion solution that kind of addresses this problem, and it helps scalability. But yeah, you do have to somehow make the knowledge available to all participants. Of course, that has advantages, because now you are not able to distinguish clients by what they know. So things like fingerprinting based on the knowledge of clients of other peers becomes not possible, and you have better verifiability. In peer-to-peer, typically these systems are designed so that you don't need to have full knowledge. So you can do with partial knowledge of the network, which means that even if you know one or a handful of other peers, you should be able to connect to the network and use it. Now, this creates enormous vulnerabilities to Eclipse attacks, because it is very possible for an adversary to target a node and to kind of try to get that node to fill their table of contacts with adversaries. And this will not be immediately visible to others, because there is no common view on the network. There's no global agreed view on the network. So it makes public verifiability very hard. It makes attacks very difficult to detect, and especially targeted attacks that are affecting maybe some high-value targets, some people. So I think, having partial knowledge can introduce quite serious problems that we don't quite know how to solve. And then another thing that I think is quite key, and it really also favors client-server architectures, is that in anonymity systems, you want to create what is called anonymity sets. An anonymity set means that this means that my transaction, if my transaction has a big anonymity set, means that there are tons of people who could have created that transaction. If you have a small anonymity set, that means that only a handful of people could have created that transaction, and that means that, you're not quite as anonymous. Now, client-server architectures, you expect servers to be much bigger than clients, so servers should be able to handle hundreds or thousands of clients. So you have orders of magnitude fewer servers than clients. So that means that these servers act as big hubs that aggregate lots of messages in an anonymity set. So you can attain high anonymity with low latency. In
Claudia,
contrast, yes?
we're actually out of time right now. Do you have one last closing thought before we transition to the next session?
Oh my God.
Sorry.
I only had 10 slides. I didn't get through them. Okay. No
worries.
I'm so sorry.
It was a great talk.
I'm so sorry. Okay, yeah.
Maybe
I'll just finish my point maybe on thin traffic. So in peer-to-peer, because you're distributing traffic over all the nodes, you basically will have very little traffic per node, and that means very little anonymity set. So that means that you can actually trace messages. Oh my God, I didn't have the clock because it's not visible in my screen right now, and I thought with 10 slides I was on the safe side, but clearly I'm not. I only made it to 7. Okay. I'm very sorry about that. I can maybe just
thanks, Claudia. This was really great.
Yeah,
if you can just drop that'd be perfect. All right, guys, check out their stuff. They're building really cool shit. Another one of their co-founders will be speaking later today as well, so you'll learn more about their project. We're going to transition to next talk now, which is
thank you very much.
Thank you so much.